AI, machine learning, etc., broadly for this year, and Leo will be leading it. And look forward to seeing many of you, and hopefully also hearing from many of you over the coming year. So the outline of the talk would be as follows. I will just show all of this so you can take a look. So we all know that AI systems can be seriously biased. So one of the interesting things we'll see is that we'll see an interesting case study from science about a couple of years ago that just focusing on the output is among other things a good idea. And then we'll talk about fairness constrained optimization, etc. Um, and then this part would be fairly introductory, but I think it'll still you know um, uh, you know put out some desiderata that we don't commonly think about. And then I'll speak about without proofs. I'll speak about work of other people and our group on what one may consider individual stochastic fairness, where we move from demographic fairness to actually, can we guarantee something perhaps probabilistically for every individual? Overall, my own take on this is that we can be optimistic that, this is a challenging problem, but that, carefully crafted formulations and, human control over parts of the process can actually mitigate not just bias in AI, but human bias as well. I'll also point out some additional resources for those who are interested. So, this we all know very well. I just pulled some numbers from 2019 because 2020 was a washout, and we all know that the numbers are staggering and that AI truly is expected to be everywhere. So, it's vital that we clearly define and implement fairness in different AI systems. So let's look at some guiding principles, which I think most of us would agree with. One is that similar people should be treated similarly, perhaps subject to relevant life experiences. So in other words, pick whatever features you feel are relevant for the particular task. And then, people with relatively similar feature vectors should be treated similarly. And of course, opportunities available to everyone. And broadly, if we have some number of major demographic features in society, we may want to keep false negative rates similar across different groups. Where you're falsely rejected for you're falsely classified as a negative. This could be in applying for loans or jobs, college admissions, etc. And in some of the situations like tax audits, you really don't want to be falsely flagged as somebody who needs to be audited. So of course, there will be individuals who unfortunately will have to go through these false classifications. But let's say that one may reasonably want that across different groups, the false positive rate for the number of people falsely flagged as positive in that group divided by the size of the group should be roughly the same across the different demographic groups that you define. Similarly, for false negative rates, etc. Right? So going back to this, these are some reasonable guiding principles. Of course, they're non-exhaustive that we may all agree upon. We'll start with two interesting cases. The second one, I think many of you may have seen. The first, I see less known in the computer science community. We'll talk about both. So we'll talk about a paper in Science by Obermeyer et al. That showed how, a certain key healthcare determination algorithm used by very large US health systems actually produces racially biased results. This is relatively recent from 2 years ago from Science. And there is an older study from CMU folks that showed that early on, when in your Google ad setting, you could set your demographic information and so on. When you set the gender to female, in fact, in general, typically you receive fewer ads for higher paying jobs. The good news is both of these have been, there has been significant progress on both. One perhaps can never say these are totally fixed, but there have been some quick responses to both, and there are good lessons to learn as well. Okay, so let's start with E1. This particular this particular issue in healthcare determination. Okay, so yes, excuse me. Yeah, so so one of the interesting things in US healthcare is as this legend says, a very small amount of the population, say 5%, accounts for nearly half of US health expenditures. This is from 2002, but the numbers have remained relatively the same. I mean, so quantitatively they're different, but the picture is very similar qualitatively. So in the left hand, rectangle, if you see the top 1%, they occupy the top 22% of US healthcare expenditure. If you go down to the top 5% on the left, that accounts for 49%, etc. Right? So clearly, large health systems are incentivized to flag high-risk patients early and give them some, so proactive health treatment, right? So this makes a lot of sense, a lot of economic and public policy sense. So an actual algorithm that is used for high risk, what is called high risk care management, where you flag people who are at high risk and immediately assign additional resources and attention for their health needs, right? Basically, as you can imagine, as the first bullet says, this clearly helps improve the patient outcome as well as the healthcare system's financial bottom line, and it's really used by very large U.S. health systems, several of them impacting truly tens of millions of people. So the way it works, and this science paper is interesting to read. So by Obermeyer et al. So the algorithm, it takes a patient's features and assigns them a risk score, and people above a certain risk are flagged for high risk care management, hopefully so that their issues can be dealt with right away, right? So what the paper showed, interestingly, is that if you take a typical, say, white patient and a typical black patient that get the same score, then the black patient was noticeably higher on the health risk scale, basically. So on average, they were far less healthy than a white patient getting the same score. So jumping ahead, there is no, it's not claimed that there is any intentional racism here. We'll see why a simple issue seems to have triggered something like this. And the paper doesn't talk about other demographic groups, so we are just talking about these two demographic groups here, right? So clearly, a very undesirable kind of issue. You can, if you, this summary article also, this output, this put out by Chicago Booth, because at least one of the authors, Mullai Nathan, is at Chicago Booth, provides a good summary. Okay, so now these pictures illustrate what we were talking about. If you look at the chart on the left, so the x-axis is you sort the patients according to the algorithm's outputted risk score, and so the x-axis shows the percentile. So for example, the dashed line and the dashed vertical line at when x equal to about 55%, everybody to the right of it are people who are in the top 45 percentile of this algorithm's risk score. So they're potentially high risk patients. And if you look at the dashed line further to the right, towards the very end on the left, that's at around 98%. Everybody to the right of it are defaulted into the program. And if you look at the dashed line, in the middle of the left chart, everybody to the right of it are referred for screening, right? And on the y-axis, suppose you count the number of active chronic conditions, then the purple curve is for black patients, and the orange curve is for white patients, right? So you can easily see that, basically the black curve lies above the white curve. So at every value of the x-axis for the percentile of algorithm risk score, a typical black patient is far more likely to have many more active chronic conditions. And in fact, they do some interesting debiasing on the right. And if you do the debiasing, then the chart on the right is only for black patients. The lower, so you only you chart you plot just the black patients on the right. The solid curve is the original is what the original algorithm specifies. So on the x-axis, again, you have the percentile of algorithm risk score, and on the y-axis you see how many fraction of the population would be flagged as having that risk score. So for example, if you look at the x-axis at 80, so at 80, at about 80, there'll be, perhaps the algorithm may say that at around this value, there may be 1%, excuse me, 0.1, 10% of the population are with this kind of risk score are black, while in reality, if you go up, you have the dash curve, which is the simulated curve after debiasing, right? It in fact shoots up to something like 30, close to 28%, right? So this work does debiasing and shows that there is this significant issue, right? So now, so why did this happen, right? So the reason is that healthcare needs are in general hard to boil down. You can of course do various tests and so on, but many issues are latent, right? So what they did is the algorithm took future healthcare costs, however it calculated it as a proxy for health score, right? Or at least a significant proxy for health score. It actually is pretty well calibrated. So in the sense that if you assume that FHCs are a good proxy for health risk, then the algorithm does pretty well. So for people with regardless of race, people with similar FHCs had similar got similar risk scores from the algorithm, right? But the issue is actually that for various reasons, black patients often are less likely to receive treatment and therefore generate lower costs when you do the FHC calculation, right? So essentially, what happens is this particular proxy is flawed. So that's the interesting takeaway from here. And the paper has a nice quote that I won't read out to you. Please take a look. It's an interesting quote. So this that it's pernicious because it can arise from reasonable choices, what appear to be reasonable choices, right? So anyway, the good news is that, so by the way, the algorithms manufacturer indeed confirmed after the publication of this work that there was this bias in a large data set, and these authors, OPVM, and the manufacturer, they came up with better proxy variables. For example, if you combine cost predictions with health predictions, simply the number of active chronic conditions, etc., they found that the new algorithm reduced bias by, at least in one measure, 86%, right? So what is one useful lesson here? I mean, this is not just an anecdotal kind of thing, but what can we take away from here, which is, output auditing and asking if the objective function, what we really want is something very important. And of course, I mean, we always need to think about unintended consequences, right? So anyway, let's keep this in mind, right? So that we need some human control over the output, asking if are the proxies that we are coming up with our objective function, because the objective as well as the constraints are really complex in the real world. We come up with some simple, perhaps some loss function or other such thing, but is this the right thing that we want, right? So this was a useful lesson from here. Again, the positive thing is that with studies like this, you can fix some of this. Similarly, if you recall the Google incident, right? On ad settings and ads for high-paying jobs, it's not that this is some very complex code, right? As for example, backprop is some off-the-shelf, a code that you just plug in. You probably, as a the software engineer at a major tech company like Google, probably writes a few lines of code and then invokes backprop, right? So, and they hire well-trained people, pay them well, etc. So malintent is perhaps not the right thing, except that as the way AI algorithms work is that they're not complicated algorithms, but simple algorithms that create models for what you want, which produce outputs in a particular context, right? So the yeah, so the two models, or at least two of the models that we can take away from this episode E2 is that we also need precise definitions of fairness in our loss functions and so on, right? So, and hopefully once you can define it precisely, in other words, if you have a constraint optimization problem in whatever neural network or other such model that you have, then hopefully one can create not perfect but better models, right? Incidentally, I would highly recommend this book, The Ethical Algorithm, that I've shown on the right, by Kearns and Roth. It came out about a year ago. It's written for the general public, but many of you who are who are well into computer science and other such disciplines, I think would also enjoy it. So I think there are interesting open questions, that will also naturally be suggested by a book like this. I'd highly recommend that you may wish to, gift it to, non-STEM people as well, because the general public does need to be educated about these, right? So far we have seen, fairness as a first class object that we may want to define in our optimization models, asking if the objective function is the right one, etc., right? So and having and having very precise definitions of fairness, right? So in the healthcare system case, if you took fairness to be that the algorithm should track future healthcare costs, it actually did pretty well. It was pretty well calibrated. But if you redefine fairness to be, are people getting the same score? In fact, the people at the same actual level of health risk. So you not just future healthcare costs, but for example, number of chronic conditions, etc. You get a very different answer. Right? Okay. So let me. So these also bring up an interesting point about the following. The book has a larger discussion about this. I will discuss it the following chart in terms of microfinance. But okay. So very often, for example, in lending, right? So for good reasons, there are certain features that you cannot take as input. For example, the applicant's race, right? So there are very good historical reasons for this. But in some cases, if you define so in cases where it's legal, the book, as well as this simple chart that I came up with, which is actually motivated by microfinance, says that in fact, it is, in the interest of fairness, where legal and possible, it may actually be better to take as many features as you want, as you can legally collect into account, except that you define you define fairness at the output clearly, and then modify your model so that in fact it does better by taking all these new features into account, right? So let's actually look at this interesting example. So suppose you let's say you have a lending problem, and you have certain positive and negative points. In this case, case, the x-axis is is the average wealth in the applicant's postal code, right? And the y-axis is the income. And of course, as you can imagine, in general, the points get as you go northeast, things get more positive. So by the way, what is this plus and minus? It's let's say historical performance of how people performed with returning their loans, right? How good the credit risk was each of these persons. So this is data that we already have. So in this case, linear classifier is perhaps a reasonable linear classifier is something like this, right? So it's not great. There are some positive points below. There is one negative point above the line, but okay, let's say it seems reasonable, right? But now, if you actually uncover a variable that you did not take into account, let's say the people are actually of two types, red and blue, right? So now you see that this classifier, this red dashed line, actually does somewhat poorly with respect to the blue population, right? So three of the blue folks are classified as negative, etc., right? So let's take a particular example that can illustrate this, right? So what's been found in microfinance is you give a bank give small amounts of loan to, let's say, typically a person in a rural or developing country context, right? And as collateral, typically these people may have too little to show as collateral, but then the whole village or some community guarantees that they return it, right? So the social pressure often has make sure that the default rate is very low, like 1% or something. I think in many banking contexts, something like a 1% default rate is considered very, very low. It's very good, right? So what could indeed be happening with the blue population is that, notice that in general, they're shifted more to the left, right? So in other words, their average wealth in their postal code seems somewhat low. But then, even people with relatively low average wealth in their postal code seem to be doing somewhat well with respect to returning loans, right? So perhaps what would be better is to have, and indeed this is what banks do. I mean, for example, commercial lending versus thrift lending or microfinance lending is done this way, right? So you don't use the same regulations you use for lending in a city to lending in a to a rural community where there is social pressure for people to return the money and so on, right. So you use two different, you took a feature that previously you perhaps didn't consider, right? And then you came up with two different classifiers, the red dashed line for the red points and the blue dashed line for the blue points. Now, of course, US college systems and so on do similar things, for example, affirmative action and so on, where they take life experience into account, right? So one of the lessons of this, so what does this say? So excuse me. So I will, yeah. So that we need precise definitions of demographic fairness, fairness constrained optimization. In fact, that you may want to take many more features into the input, which seems to go in the direction opposite to fairness, where fairness should in general be oblivious to various features. And that's an important consideration, of course. But the question is, perhaps the point is where, that this previous chart tried to make is that we may be better off by taking more features into the input, but then defining what fairness means at the output, right? So filter at the output, right? But then on the other hand, there's also bad news, which is that if you look at, reasonable, just like with Arrow's theorem, there are, impossibility results. For example, it's well known that if you take three reasonable desired qualities of a classification system, for example, approximate equality of false negative rates across different demographic groups, approximate equality of false positive rates, again across different demographic groups, of positive predictive value and so on, then there is no, unless other than trivial solutions, trivial contexts, right? There is no algorithm that can simultaneously satisfy all, right? So what this means is that society needs a strong. You can't let it be a totally AI run decision making system, but that society needs a strong role. And finally, like to say once more, like the previous linear classifier stuff said, more important than restricting input features, which a priori looks like the right thing to do in order to enforce fairness, more important may be output auditing. In other words, add whatever features you can legally and practically, to the input in order to construct your classifiers, but do output auditing to see, for example, if in lending, if let's say your primary focus is approximate equality of false negative rates, right? Take whatever legal features as you want in your feature vector, but just make sure that this particular fairness criterion, which is approximate equality of false negatives, is false negative rates, is preserved across your different different demographic groups. So this is something I think doesn't get too much press often. I mean, people naturally think about restricting input features, but the previous example shows that may not always be the case. So where legally possible, output auditing is perhaps better than restricting input features. Okay, so far we have spoken about group fairness, right? So we have talked about groups on aggregate, not individuals. But is group fairness, sufficient, right? So there is an interesting quote by Sidney Morgenbesser. He was a professor at Columbia, and he has some interesting anecdotes. Take a look at this. He said that when he was hit on the head, he said it was unjust because they hit me, but it's not unfair because everyone got hit, right, by the police, right? So in other words, so suppose an algorithm can make the reasonable claim that it's demographically fair across different groups, right? But suppose I am part of a group G and I was genuinely unjustly classified, let's say, right? Then it'll be cold comfort for me to be told that unfortunately you had bad luck, but then your group did fine overall, right? So while I may be happy that different groups were treated reasonably similarly, I would ideally want something guaranteed to me as an individual as well, right? So how can we go beyond group fairness? This is the segue to the stuff that my collaborators and I have been doing. Um, yeah. So can we promise individual level fairness, right? Now, of course, you can't, make everybody happy. Resources are limited. You can't make everybody happy, and this is where randomization can play a useful role, right? So your algorithm is randomized, and then it has verifiable stochastic fairness guarantees on a per user basis in an easy manner that we'll see soon, right? If your algorithm is of a certain type, it's very, very easy to write a few line piece of code that can take any algorithm that claims to give individual stochastic guarantees, and take that algorithm as a black box, and this few line piece of code along with a publicly trusted lottery can easily verify that this piece of code is indeed is indeed accurate in making this individual fairness claim. So, okay, so we will focus here on certain topics in unsupervised learning, specifically clustering, which, as you know, is ubiquitous in unsupervised learning, right? So typically you're given a parameter k, and you want to cluster your data, for example, on the right into, say, three colors, green, red, and blue, right? And in this case, k is equal to 3. K will always denote the number of clusters. So one objective could be that you want to keep all the cluster radii small. That's called the k-center objective. So what is the so k-center is a global objective, right? So what it says is that nobody has to travel. Okay, so it's also a local objective, right? But in the sense that it puts an upper bound on the distance from any point to its cluster center, right? But points can still be misclassified, so that is a bit of a danger. They could be far from their cluster centers, so their cluster doesn't make too much, is not too meaningful to them. For example, these red points that are at the boundary of the red cluster, not far from the green cluster, may be better off, perhaps, they probably have more commonality with the blue point, with the green points, right? That's possible, right? But the biggest point is they could be cast as outliers, right? So there are several points here, the points that I've drawn outside that are not, obviously in the three clusters, as outliers, right? So now usually you may have some amount of budget to deal with some number of outliers, right? You can say, if I have a data set of 10 million points, I will, and if k is 50, I will classify almost all my points, and I'm happy to handle about, say, 1,000 points as outliers, right? But not more than that, right? I can give, individual treatment to them in whatever way, something like that, right? But once again, the issue is, that's pernicious. If you just view algorithms as code, algorithms as black boxes, is that in multiple runs of this algorithm, the same point or same demographic type of point may keep getting classified as outliers, right? So they may get poor service in whatever way, right? So, for example, let me put up some previous work. This is from two of our current and former UMD colleagues, Dave Mount and Samir Khuller. So they considered this problem. This doesn't talk yet about individual fairness. We'll come to individual fairness in a minute. But how do you at least handle, say, outliers in for example, the k-center problem? So there, they take three parameters as input. One is k, the number of clusters. Second is you want a lower bound t on the number of non-outliers. So there are n points. You want to classify at most n minus t as outliers, and you also have a target maximum radius r for every one of your clusters, right? What they show is that you can efficiently solve this problem. In other words, you can cluster the points into k clusters. The number of points that are clustered is at least t, but the maximum radius will not be r, but at most 3r, right? So it's an approximation algorithm, but at least it satisfies the requirements on k and t exactly. It doesn't approximate those. And this was improved by Chakrabarty et al. To the optimal value of 2. Doing anything below 2, even without the outlier condition, is impossible in polynomial time unless p equal to np, right? Okay. So, like I said, however, what about individual fairness, right? So, specific points can repeatedly get classified as outliers. And recall that one of the principles we started out with is that similar points should be treated similarly. It could be that there are these two nearby points, while a lot of the time this gets classified as an outlier, but for no strong reason, a very nearby point most often does indeed get clustered, right, into a meaningful cluster, right? So how can we guarantee individual fairness? There are many different approaches to individual fairness. I'll just talk about one particular approach my group has taken, and it's not meant as exhaustive. Okay. But what is the high level idea? The high level idea is allow your algorithm to be necessarily randomized, right? And then make per user probabilistic guarantees, right? And then guarantee every user J that only with respect to the randomness in the random choices made by the algorithm are not depending on any probabilistic assumptions about the input, right? Therefore, for every input instance, and only with respect to the randomness related to the random choices of your algorithm, you get some certain level of quality of service with a certain guaranteed probability, right? So for example, consider this formulation. Other formulations are possible. We'll talk about them, right? So the first two are basically the same as the first two bullet points are the same as what we spoke about before. But third, suppose you now have a service level agreement for every user J, right? That they get clustered and therefore into a cluster of radius R or 2R or something, right? With probability at least a contracted value Pj. We'll talk about these Pjs in the next slide, but suppose these Pjs are given to you, right? So, and again, this probability in the left-hand side is only with respect to the random choices made by your randomized algorithm, right? So suppose you want this, right? So there is some work I did with my former students, Harris, Pencil, and Trin. For instance, one of the results from that paper is the following. We give an efficient randomized algorithm, which will either certify that it's not possible to satisfy all of these constraints, including these probabilistic constraints. It will either prove that's the case through a linear program, or for any given positive constant epsilon, it'll find a clustering it'll find a clustering where the number of clusters is k with probability 1, the max radius is at most 2r with probability 1, and instead of clustering at least t people, it'll cluster, say, at least 99.99% t people, right? So with probability 1, all of these, in other words, for every run of the algorithm, this will be true, right? And second, at the individual level, for every user J, the probability that they get clustered meaningfully is not exactly Pj, but at least 1 minus epsilon times Pj. Now, something here may look suspect. Everything here is all the guarantees seem to get only better as you make epsilon smaller. So why can't you take epsilon to be 0? That's because the runtime of the algorithm is a function of epsilon. Right? It's an increasing function of 1 over epsilon. Right? So yeah. So yes. So this is a sample theorem. So notice that this allows some global guarantees. For example, something about t, which is the number of people that you are guaranteed to put into reasonable clusters, right? And the number of clusters k, etc., as well as local guarantees that are on a per user basis. For example, the maximum distance they have to travel is at most 2r, and not just that, the probability that they get into such a meaningful cluster is at least 1 minus epsilon times their contracted value, right? So therefore, we view, including randomness explicitly into your algorithm as one way of guaranteeing individual probabilistic guarantees, while of course also making some global guarantees, right? Okay, so now let's continue. So how can you, if the PJs are not given, you can take them to be some fair common value. For example, this is a reasonable value, right? So how do we interpret this probability, right? So, okay, let's go back to the previous slide. Look at this 1 minus epsilon times Pj, right? Okay, so again, what every user is told is the following, right? Is that this algorithm will make random choices when it runs. And when it's finished, you are guaranteed a cluster of radius at most 2r with probability at least 1 minus epsilon times Pj, right? So how do we interpret it? The easy interpretation is the frequentist one, which is that, of course, we interact with these algorithms, these clustering algorithms all the time, right? So, for example, we may be a user, applying for loan decisions from multiple agencies. In other words, such an algorithm is repeated independently by for multiple iterations, or we could be a customer receiving, ads on the internet, right? And if such an algorithm is run, I hope to receive meaningful ads at least a large number of times. So that's the natural frequentist interpretation. If 1 minus epsilon times Pj is 40%, then I know that 40% of the time at least I get reasonable service. And I interact with these systems multiple times. In the case of internet ads, numerous times, even even over an hour's period. So on average, I get reasonable service, right? But this makes sense even for one-shot algorithms, and that's easy to see why, right? So even for one-shot clusterings, it makes sense because you can just do the following, right? So again, suppose Pj is like 40%. So take 1 minus epsilon times Pj also to be like 40%, just for simplicity, right? So, or 38% or whatever, right? All you need to do is, you have this black box algorithm, repeat it a large number of times, say 100,000 times, and publish all the clusterings, right? And every user, a simple piece of code at the user verifies that they are non-outliers in at least 38,000 or 40,000 of the clusterings. In other words, at least 38% of all the clusterings. And now use a publicly so there are these 100,000 published clusterings, right? Use a publicly verified lottery to pick one of these at random, right? Then every user knows that if they did not get what they want, a good cluster, right? It's only because of the vagaries of chance, not because the algorithm had something shady or miscoded, etc. Right? So it's a very simple, a tiny piece of code that the user has to do, and the algorithm itself can just be a black box, right? So this kind of guarantee may therefore make sense even for one-shot clusterings. And so the fact that this second bullet works is due to simple large deviation bounds like the Chernoff bounds and so on. Right? So this is one approach to fair outlier handling, and there is some more such work. For example, you can also ensure that your distance to your cluster center is guaranteed to be at most, for example, this 2R with probability 1, but even smaller in expectation. And again, the expectation is only with respect to the randomness of the randomized algorithm. And then there is some further other work on clustering with fair representation, where every cluster gets reasonable representation.
Aravind, excuse me, Furong has a question for you.
Okay. Hi, Furong. Furong, please go ahead.
Oh, okay. The question actually was. Oh, okay.
Sure.
Yeah.
Oh, sorry. I just have a question regarding like the incentive for fair chance of being an outlier in a randomized clustering algorithm.
Okay. Sorry, incentive for?
Oh, so why do we want it to make sure that the outlier, each data point will be an outlier with an equal chance?
Oh, I see. Okay. Yeah. So that's true. So, okay, don't think of it as outliers. Okay, so some people will get good service. In other words, they'll get a cluster of radius at most 2R, right? Which is a good service, and some others will. So in general, your data set is such that, unfortunately, if you have to classify them into K classes, you cannot guarantee, the data is simply such that with some number of outliers, you cannot guarantee to everybody that they will lie in a cluster of radius 2R. Right. So the question is, which of them do if the data is somewhat dispersed, which of them do you determine as outliers, right? So that decision can be somewhat arbitrary, right?
Oh, you wanted to make sure everyone gets a chance of being clustering correctly with high confidence interval in this clustering algorithm.
That's right. Yeah.
Okay, gotcha. Thanks.
Thanks. Yeah. And yeah, thanks for the question. So, I mean, the question also, brings up a point. So again, the PJs may not be explicitly obvious. You can, for example, say that the sum of the PJs should be at least so much for every demographic group. The point is, if you have these individual stochastic guarantees, then at least in expectation, it's trivial to lift them to groups just by the linearity of expectation. If you have individual stochastic guarantees like this, it's very easy to show that, if you have, again, different demographic groups, they'll all do pretty well in expectation, right? So this is the individual case is the more general case. So we have, some other such results as well. So so also in a couple of papers, recently with Leo, who's the host here, and other colleagues, Brian Brubach, who's a student and is now a professor at Wellesley, Darshan Chakrabarti, a student at CMU, a graduated student at CMU, John Dickerson, who's here, Samir Khuller, our former chair, and Leo. We have a couple of papers I mean, the subsets of authors are slightly different, but basically we look at cases where you have some side information, some side probabilistic information about how similar nearby people are. And in general, we want to cluster similar people similarly. For example, busing similar students from the same street to the same school, and to avoid harmful intent like gerrymandering election districts, etc. So we have some further work on these, and again, many of these come with individual guarantees. In this case, pairwise guarantees. So still local guarantees in addition to the typical global guarantees. So by the way, a lot of this research proceeds by convex programming relaxations and new rounding approaches to guarantee fairness. One very nice paper I found recently is by Makarechev and Vakilian on ensuring diversity in clusterings and so on. It's very interesting work, both from a formulation point of view and an algorithmic viewpoint. So I didn't say much about how we do this at all. So, but this is very briefly the technical approach that we take. So, just to summarize what we have said so far, we came up with some general principles for group fairness. For example, output auditing, and in fact taking as many features as are legally and practically possible into the input, but carefully auditing the output, and defining fairness precisely, fairness constrained optimization, etc. Right? So we started with that, and then we have been looking at these more individual stochastic guarantees, where if you want to, you cannot in general please every individual simultaneously, but you can please them in a stochastic sense. Right. So this is some representative work from our group. Let me also point out a few other papers that, if you're interested in individual fairness, there is this classic work of Cynthia Dwork et al. On treating similar individuals similarly from the ITCS conference 2012. There is some interesting work by Kearns and Roth and their former student Sharifi Malojeddi from NeurIPS 2019. Also, Ilvento, who's a student of Dwork, she has some interesting work in, so we said similar people should be treated similarly, right? Okay, so that's fine. But how do we learn? What do we formally mean by similarity? Of course, you can naively take distance between their feature vectors and so on, but can we do better? And she has some interesting work on how to learn a good metric from a data set to a distance metric or its opposite similarity metric in order to infer such similarities first, so that your algorithm can then operate on the similarity metric. Right. So these are just some, again, as it's a rapidly growing area, and this is just a small selection that I think will be of interest to many people here. So I also want to, again, the other, one other thing that that excites many people is that AI can help combat human bias, right? So there is of course low-hanging fruit that many of you would have heard about. It's almost a cliche now. For example, there was a study that said that judges typically give harsher sentences if the sentencing time is just before lunch. I mean, presumably they're hungry and impatient and so on. So obviously this is a kind of, so if a person was unlucky to receive their sentencing just before lunchtime for the judges, then the fact that can have such a life-changing impact on them is unacceptable, right? So similarly, for instance, only about 3 years ago, I learned the difference between jail and prison in the US justice system. So jail is when you're held before a trial, and prison is if a person is found guilty and then put in prison, right? Now there is a very high stakes decision about so when a person appears for bail, for the judge to decide very quickly whether they should be put in jail for about 2-3 months awaiting their trial, or whether they're able to go out on bail. For many people, as you can imagine, this is an absolutely life-altering decision, because if a person is low income and if they have to not attend their job for about 2 months, they'll likely be fired, and the economic and other consequences are devastating, right? But so there are many such cases where AI can very fruitfully combat human bias. There is this classic study, Bertrand Mullainathan study. I will go, in the interest of time, I'll go over it a little briefly. In short, they found that for help wanted ads in the summer, for for jobs that did not require too much training. For example, you could be a this was 2003, but let's say a call center operator, you could do it with, let's say, a 10th grade education, right? So not too much background was needed, right? They found that even if the resume is very similar, just changing the name to a white sounding name versus an African American sounding name made a significant difference in callbacks and so on, right? So now the point is not just to complain about it, but so this identifies a problem, and AI kind of stuff can very easily combat this kind of thing, right? Because you can debias, you can just in this case maybe take away the name from your list of features. This goes against what I said before, which is to include more features, but or you can retain the name, but give more weight in your neural network to prior experience, etc., right? Similarly, again, on a positive note, there is work on and in fact Alan Fries gave a colloquium talk here, I think in 2018 or so, on algorithms to rigorously detect gerrymandering. My own group has done a little bit of work on this last year in EC, but so this again, so I just want to as we come to the end of the talk, I wanted to say that in fact it's not just that there is stuff to fix in AI systems, but AI systems can help, of course, combat human bias as well. Starting with the low-hanging fruit, like judge inconsistency over the day, but to much more sophisticated issues, rigorously proving gerrymandering, etc. Right. So again, so the principles that we see are, if you can define fairness and audit the output, like we have been talking before, it can greatly help mitigate such bias. I will just point out some additional resources. This book, which, like I said, is an excellent book. FACT is a good conference, as is FORC. There are many people doing excellent work in this field. I'm only putting out a subset here. I mean, this is not representative of the field, but it's more representative of my understanding of the field. These are the folks whose works I follow a lot, but you can start with their work and branch out into other related literature. So to summarize, I will say I'll say what I started out with before. That with a few more rigorous definitions, one can go a long way, and also one can go, in fact, from the more coarse goal of demographic group fairness to actually individual fairness, but you will almost always have to necessarily involve stochasticity in the process, because you can't please everybody. And I'd like to end on an optimistic note that, in fact, I think that our carefully crafted AI systems can actually bring very constructive social change. Let me stop here, and Furong already had a question, but happy to take other questions. A few people said that they'll ask questions offline after the talk. I'm looking forward to that as well. But if you had others, please ask now.
Thank you, Arvind. Anyone having a question, send me a private message and I'll forward it to Arvind. I'll unmute you actually, so you can ask it yourself.
Okay, while people are perhaps thinking if they should ask, let me point out a couple of things that I didn't have time to talk about. In the interest of time, I didn't mention this. So this is a shout out to John, Leo, and others. So they have some work last year. So we spoke about say fair classification, etc. Right? But sometimes certain attributes may be protected, right? In some, for example, race is a protected attribute. Although,
sorry, Arvind, there is an incoming question.
Sure. But I'll just finish saying this, and then happy to take the question. So, but then, so you may only be able to infer it probabilistically, right? So if you want fair representation, etc. What if you only have probabilistic information about some of the features? There is work by John, Leo, and others from, I believe, last year's ICML on handling some fair classification problems under such uncertainties. The one other thing I would add is that, my own group has also been working on, fairness in computational epidemiology, in social distancing, vaccination, and so on. with Leo and others on how you can ensure, for example, vaccinations. Of course, there is the natural thing that you want different demographic groups to be able to access it quickly at times of a pandemic. And with social distancing, again, if you have a blunt instrument like nobody should attend a school, or other such things, or does social distancing impact some groups more than others, and how can you mitigate some of this, is something that my group and I have been interested in, and we have been working on, including some undergrads here as well, like George Lee. Okay, so I'll stop with these two, and happy to take the next question.
Hi. So I want to ask, so in recent conversation, at least in media, there's a lot of emphasis on privacy with like GDPR, CCPA, with big tech and everything. But some of the examples that you provided here suggest that perhaps we need to collect more information or more information about certain demographics to ensure fairness. So do you think that there should be more focus on protection versus privacy, given that we might actually need some of this more sensitive information to make sure that to ensure that there is fairness?
I see. Yeah, thank you. So that's a very important point. So the interesting thing is, as you know, if you look at privacy and fairness, right? So which are two, of course, very important, desiderata. For privacy, differential privacy has more or less emerged as the victorious formulation, and there is increasing work on. So while with fairness, as we already see in this talk, that there are many different definitions possible, etc. Right. So some of our own work is on, as you said, on for example, in the epidemiological context, can we have differential privacy for instance, if people have to reveal whether they're sick or not, whether that particular bit can be kept differentially private, right? So I'm sure all of you know about differential privacy, but if you don't, very, very important modern tool for defining and implementing privacy. So my long-winded answer to you, Simin, is yes, there is active work on combining some of these fairness guarantees with, for example, differential privacy. I don't know of other rigorous ways of handling privacy other than differential privacy, but happy to talk more offline as well. And just to again to repeat what I said, there's been very significant progress. Again, if you look at these many of these conferences or work of Cynthia Dwork and others, you'll see that, or Aaron Roth and others, there's very significant progress on all kinds of combinatorial optimization and other such and settings like this, where you also want fairness, that at least certain attributes can be kept differentially private.
Thank you.
So by the way, there is a nice online book on differential privacy freely available by Cynthia Dwork and Aaron Roth. There is also an excellent YouTube class from Waterloo by Gautam Kamath. If so I can send me email if you're interested. I can send you these links.
All right, thank you.
Welcome.
Any other questions?
I was gonna ask, like, so there are multiple notions of fairness and such as in privacy, but like now we are seeing some regulations for privacy, like the US Census, for example, is using differential privacy. My question is like, where are we standing in terms of government regulations to enforce these like notions of fairness to in practice? Is there any effort to regulate these, or we are far behind in regulations?
I see. That's a good point. Yeah, while we have made more progress in privacy, I think there is much less in fairness. I think it's pretty ad hoc to the extent of my understanding. I'm sure there are a few regulations, but by and large, it's still I think it's up to us to actually, the research community to show that a lot of improved fairness is possible. For example, the Obermeyer et al. Study from Science it didn't come top down at all. These people, Obermeyer is an interesting person. He's a professor at Berkeley, but he's also of I think public policy or public health, I forget. But he's also an MD, and in his spare time, in his spare time, he spends time, about 1 week a year working at a hospital for Native Americans or some, or some underserved population, I forget. So, it was lucky that I think maybe it was through this contact that they found that there was this particular massive discrepancy. So in general, so I think that there is very little oversight coming from top down, and that's perhaps a good idea. I think it's better for us, the research community, to take the lead in this. But it's not just the research community. The tech companies are highly interested in this. So so overall, I think that the effort is still bottom up, but I see it happening. And among the first things we could do is to bring more rigor into the study, defining these things carefully, coming up with trade-offs, impossibility results, all of these things. In short, I think we know much less about regulation of fairness as compared to the regulation of privacy.
Thank you.
Aravind, there is one final question.
Hi, I have a question. This is Mohammed. So I was wondering if, you showed some graphs about fairness between classes like whites and blacks, and is there any other effort into fairness within a class that can transcend across these different classes? Because if there are some major differences within a class, then that can cause a bias, and you may not see actual fairness ordeals or biases that creep in within the class when you look at the bigger picture between two big classes, large classes.
Yes, that's a good point. But although not that, yes. So for example, if you coarsely, classify everybody as according to a certain race, you're not taking class into account or their individual wealth at all into account, and which can make a massive difference in life outcomes and other choices. So yes, but Mohammed, so note that our definitions are abstract and just say certain demographic groups. They don't say it's whether it's race or gender or things like that. So it's up to you in your context to define what your what your demographic groups are. In general, of course, they'll overlap, which is important. So you can, for example, take a multidimensional view that you partition them say according to race, according to class, according to urban versus rural. You can slice it multidimensionally like this. So all these algorithms, their runtime is, say, often it doesn't depend terribly on the number of demographic groups at all. So if you have, for example, say in the US, in a country as large as the US, let's say you have an algorithm with, say, 100 demographic groups according to these different slices you want to do. I think that will be perfectly reasonable for many of these algorithms.
Thank you.
We have
if
one
there's
more
time
question.
for one more question, yeah.
So I'll try a short one. Thanks, Aravind, for a good talk. You point out in the conclusion that human input is essential, and I couldn't agree more. And I'm curious to know how you think about this human input, like what form can it take, and who are these humans that we should be asking input from?
I see. Yeah. So I meant it broadly as that public policy shouldn't just be shouldn't be left to so we formulate these objectives and solve them, but is this really satisfying what we want as a society? So I meant it in that broad sense. And in fact, somebody like you probably knows better than me about which people should be involved in it. I don't have a good answer to that, but I think you see the broader point I'm making, which is, we need to, especially in the light of impossibility results, right? So, for example, like we saw, you cannot simultaneously satisfy demographic parity on false positive rate, false negative rate, and positive predictive value. So you could say that, so by human input, for example, what we mean is, in a particular setting of these three, which two or which one is the most important for you, right? And that being made public. and that being something that is a socially accepted norm or a legislatively accepted norm or something like that. So I mean, this is just to combat the inherent trade-offs that we have to make in even formulating what fairness is. But I don't have a very good answer to this, and I'm happy to chat with you offline. In fact, a few people wanted to chat offline, which I'll do right now. But Marine, if you had some thoughts about this, I'm also happy to talk to you offline.
Any other question? I think we're out of time also, so we should better stop here. Aravind, thank you again for giving the first talk. We'll have another talk next week. You will receive an email soon. And hopefully this is going to be a great seminar series.
Okay, thanks, everybody.
Thank you all for attending.
Bye.
Bye.